In this video, we will study about the derivation of Klein Gordon equation. Okay, so it's a very important equation in the domain of relativistic quantum mechanics. In order to derive it, we are going to use the energy momentum equation from special theory of relativity, and this is E square equal to P square C square plus M square. I should write M naught square C4, but for convenience subsequently I will write m naught as m, and this is rest mass of the particle, this is momentum, this is the speed of light, and this is the energy. Okay, all right. So to proceed further, I will use the operator corresponding to uh, these uh, energy, momentum. Okay, so energy operator, this is given by iota h bar del by del t, and momentum pressure, this is given by minus iota h bar this del operator. Okay, so I will insert these two operators in place of energy and momentum. So from this equation we will have iota h bar del upon del t whole square equal to minus iota h bar del square c square, and here m square c4. Okay, and now if you square it, so iota becomes minus 1, a square of iota is minus 1, so it will be minus h bar square del square by del t square. Okay, and similarly here it will be minus h bar square del square, I will write c square this side. Okay, so remember that the c square constant, so it's better to write c square on the left plus m square c4. All right, so we'll simply simplify it further, and so let's divide both sides by h bar square, so this will get cancelled and we will have minus del square by del t square, and this is equal to minus c square del square plus m square c4 by h bar square. So you just bring it this side, so we will have del square plus cl this and minus m square c4 by h bar square equal to 0. So I will just write down the final simplified form. So look at here, this combination of operator, this is equal to this box operator, and this is called D'Alembert operator. Okay, so we can write this as this, okay, plus m square c square by h bar square. Okay, and equal to 0, but this does not make sense, it's just operator, so we apply this operator on some function, so we put psi here, and this side it will become 0. Okay, so now look at this. Usually in many textbooks you will see that they are using so-called natural units, in which c is equal to h bar equal to 1. This is called natural unit, so remember it, natural units. Okay, so if you put c is equal to 1 and h bar equal to 1, so this will become simply this box operator plus m square into psi equal to 0, and this is the Klein Gordon equation. All right, so the important thing, the important properties of this equation is that This equation is Lorentz invariant. When you make Lorentz transformation and this equation, this will be invariant. Okay. And the second thing is that this is a very simple equation, and it's the realization, that a Schrodinger equation is not Lorentz invariant, so it fails to describe the relativistic particles, I mean the particles which move close to the speed of light. But this equation works pretty well to describe the relativistic particles, but it has its own limitations. It fails uh, to describe the relativistic domain. Okay, so and that means this is not so accurate equation, and why I will tell you in another videos. Okay, so I hope you understand it. Thank you. So keep watching, and I will make another video and subsequent topic. Thank you.